Hi everyone, and welcome to your video, your video titled Related Rates, the Cone. So up until now, we've been studying related rates, but we've really only focused on those sliding ladder problems. So today we're going to tackle a new type of related rate, which involves a cone. So in the beginning here, I did give you two little geometry splashes because I'm not sure how much you remember from geometry. The first geometry splash says, two figures that have the same shape are similar. So you studied similarity in geometry. So if they have the same shape, they're similar. The ratios of the lengths of their corresponding sides are equal. So that will come into play in just a minute. The second geometry splash is that the volume of a cone is given by V equals 1/3 pi r squared h. So I'm going to highlight over that too. So just food for thought. Okay, moving into the problem. Let's go ahead and read it. It says water is pouring into a conical tank. That's a tank shaped like a cone at the rate of 8 cubic feet per minute. If the height of the tank is 12 feet and the radius of the circular opening is 6 feet, how fast is the water level rising when the water is 4 feet deep? Okay, so the first thing, and you can see I've set up my sections here, the first thing I always like to do is draw a diagram. So I am going to draw a cone, point down, because if water is flowing into this tank, then we have to have the circular opening at the top. So this will represent my cone-shaped tank. And they did tell me that on this tank, there are two fixed values. And remember, just like the length of the ladder, any value that is fixed, we may put right onto the diagram. So the height of this tank is 12 feet. So I do know that I can put 12 right here. And the radius of the circular opening of the tank right here is 6 feet. So I'm going to go ahead and put those measurements on right away. I also know that water is going in to this tank. So I'm going to draw, let me actually get blue here, if my blue pen will work. Here's my water. I'm just going to draw some water in this tank and I'll color it blue. So as the cone starts to fill with water, we have some changing values. The height of the water will definitely be changing. It'll be increasing. And the radius of that water surface will also be increasing as we start to fill. So I can't give R and H right here numerical values because they're both changing. Once I differentiate implicitly with respect to time, then and only then may I plug specific values in for R and H. But I have to let them vary as I go through here for now. Okay, so what else have they given me? So I used the 12 and the 6. We'll kind of highlight over those. So I've got that, I've got water. So let's write down any other givens that we have. Well, this 8 cubic feet per minute is given, so let's figure out a label for that. The way I always figure out my label, meaning I know something is given to me that's 8 cubic feet per minute, but what do I call that? Well, I look at the units. Cubic feet is volume, and minutes is time. So this 8 cubic feet per minute is my change in volume of this water with respect to time. So the change in volume with respect to time is 8 cubic feet each minute. So we fill 8 cubic feet with every passing minute in this cone. So that's a given. The only other number that I'm given in this reading is this 4 feet. And so what is that? Well, how fast is the water level rising when? So at the moment the water is 4 feet deep. So when this height is 4 feet deep. So they are giving me an H value, but again, I can't plug that in. It's It's not like I can go take that and put a 4 here. That will come into play later after differentiation. Once I figure out how quickly R and H are changing over time with these givens, then I can plug that in. But I'll write it down as a given because they did give it to me. Okay, what do I need? What's the question? Well, I usually like to find the question mark, which is right here at the end of the sentence here. So what I need is, how quickly is the water level rising? So how quickly is H changing? Okay, so I need the change in the height of the water with respect to time. And my units for that, I'm going to put a question mark here. My units for that, well, height will be measured in feet. And time in this problem is measured in minutes. So that's what I'm looking for. Okay, so I need an equation that's going to relate H's, V's, and a cone. H's, V's, and a cone. H's, V's, and a cone. Well, I'm going to come right back up here. Here's an equation that involves a cone. It has a V in it. It has an H in it. It also has an R in it, and we'll deal with that in a second. But the equation that I'm going to write that relates all these variables is the volume of a cone equation. So volume equals 1/3 pi r squared h. Now, we have a slight problem. They did not give me any information about dr dt, like how quickly r is changing. And if I go ahead and differentiate right now implicitly with respect to time, I will end up, because of the product rule, I'll end up with a dv dt over here. And when I run the product rule with 1/3 pi r squared as my u and h as my v, I will end up with a dr dt, and I have not a piece of information about dr dt. So my next mission is to go down here to my side work. I want to try to get the volume equation in terms of h only. I want to try to get rid of this r, and there really is a simple way to do it, and it has to do with this similarity we talked about up here. So if you look at this cone, check out the similarity going on. Let me try to change color here again. Let me get my, maybe like a red pen here. So if I look at this 6 and this 12, if I kind of turn that into a triangle right there, and then I look at this r and this h and turn that into a triangle, I've got myself a set of similar triangles right here. And when you have similar shapes, the ratios of the lengths of the corresponding sides are equal. So my side work is going to look like this. I can say that 6 is to r, so I'm going to set that up, 6 over r is equal to 12 over h. You probably remember doing this in geometry. So 6 is to r as 12 is to h. See how I did the ratios of the corresponding sides of the similar triangles, and I set them equal to each other. Once I have this, I can cross multiply. So if I cross multiply, I'm going to have 12 times r equals 6 times h. And now I can solve this equation for r by dividing both sides by 12. And when I reduce, I get that r is equal to 1/2 h. Now, the beauty of that is I take this back up to my equation. Where the r is, I'm going to replace it with what r is, which is 1/2 h. So it will look like this. Let me change colors here. So I have v equals 1/3 pi. Here we go. I'm replacing r with 1/2 h. Now I still have to square that because r is squared. H. Now I've got my volume equation all in terms of H, and that means that when I implicitly differentiate, I won't have a dRdt. I'll only have a dV/dt and a dH dt, and I've got those going on over here. Now I will do a little algebra here. I'm going to do some exponent work. If I take 1/2 h and square it, then I get 1/4 h squared, and then I still have that h on the back. And so my final fixed up equation here for volume, if I multiply 1/3 times 1/4, I get 1/12. And then I have my pi, and h squared times h is h cubed. So 1/12 pi h cubed is going to be my equation. All right, now I'm ready to differentiate and bring in time. So I'm going to click and drag that down here. So v equals 1/12 pi h cubed. Okay, so now I'm ready to implicitly differentiate with respect to time. Remember, you're going to differentiate each term with respect to time, which means you differentiate and then tack on d whatever dt to the back. So we talked about that with the ladders. So here we go. The derivative of v. Well, the derivative of v is just 1. But then I must tack on dv dt. On the right side, this is actually just the power rule. If you think about it, look at this. The 1/12 pi is just a constant. So this is really no different than having like 5h to the third or 3h to the third. 1/12 pi is just your constant. So when you run your power rule, you're just going to bring the 3 to the front. So you're going to take 3 times that constant, 1/12 pi. And then you're going to take your h and subtract 1 from your exponent, which turns it into an h squared. Tack on dH dt. Okay, so cleaning this up, 1 times dV dt is just dV dt. And I can take 3 times 1/12, that's 3/12 or 1/4 pi h squared dH dt. All right, and then when I look at what I need, since I need dH dt, I'm going to go ahead and finish this and solve this equation for dH dt, which means I'm going to have to divide both sides by 1/4 pi h squared, which will cancel those out. So my dH dt is going to be equal to my dV dt all over 1/4 pi h squared. Okay, now I'm ready for my plugins and my solving to finish this problem. So I'm going to bring this up here. I'm going to write dH dt first equals. Okay, dV dt, I have that up here. dV dt is equal to 8. So that goes on the top, all over 1/4 pi, and now my h. See, I wanted how quickly the height of the water was changing. At the moment, h is 4 feet. So that's what I'm going to plug in for this h, 4 squared. And so dH dt, now I'm going to grab my calculator over here. And so if I plug this in just as it is, alpha y equals, enter. I've got an 8 on the top. On the bottom, do another alpha y equals 1/4 pi parentheses 4 squared. Okay, so I'm getting 0.637 if I round to thousands. And units, remember from up top, height, feet, and time, minutes. Okay, so there's my answer. Now I'm going to finish this by writing my sentence and kind of putting the finishing touches on this, okay? At the moment, the water is 4 feet deep. the water level is rising, hence the positive value we got for dH/dt, is rising at the rate of 0.637 feet per minute. And the thing I love about the cone is that it's so clear when you're looking at a cone why the rate depends on the depth. It's a little bit easier to see than in the ladder problem, because with the cone, because of the nature of what a cone looks like, in the beginning, like when the height of the water is very small, the rate at which the height increases will be faster because you're not filling up as much space down here at the tip of the cone. But you can see that as the height increases, it will take longer for the height to change because you're filling up more area up here. So my guess would be that if I plugged a different depth into my dH/dt, this value will decrease because we should slow down the speed at which we fill, the speed at which the height grows should slow down the higher we get in the cone. And I can test that really easily. All I have to do is plug in a taller height of the water. So I would do my 8 and I would do my 1/4, that all stays the same, and my pi. But if I plug in maybe 6 feet deep, oh, I forgot to square it. I was like, well, that didn't work. Forget that. Hold on. I forgot to square it. I forgot to take the h squared. I thought, uh-oh, everything I just said isn't true, but it is. Okay, 8 over 1/4 pi 6 squared. Yeah, see, when you're 6 feet deep with water, your height is only changing at a rate of 0.283 feet per minute. See how it decreased? So hopefully that makes sense. Okay, so you're done with this video. Now the next video on the cone is going to tackle the problem on the back. So tune in for that if you were absent from class.